Alright, hello and welcome back. Um, we just fix some things quickly and we'll be ready to go. Yeah, so today is Wednesday, and that means we will be doing some calculus tonight, so I'm really looking forward to that. Um, got a nice lesson for today, and yeah, I don't think there are too many announcements for today, so we'll get into the content really quick. As a reminder, today is calculus, tomorrow will be physics C, and as always, if you can't tune into the Twitch live streams, you can always catch us on YouTube at Probopolis. So last week we introduced the concept of derivatives, and we started to learn how to compute derivatives, but first we learned that derivatives are a measure of the rate of change. Additionally, they measure the slope of a function at a particular point, the slope of the tangent line. So those things are really important to know, not only for last lesson, but also for this lesson, and basically all future lessons that we'll have. So we introed derivatives. Today we're going to get more into derivatives, learn some new techniques to calculate derivatives, and yeah, it should be a good time. So let's get into it. All right, so I think we left off here last week. And if you didn't see the previous lesson, you can always watch that. It's the last calculus video. All right, so today we're going to talk about the chain rule first, and this one's really important actually, so it's nice that we're starting out with it. And the definition is below. I'll read it out loud, but it can be a little bit confusing, so we'll really try to dissect what's going on. So we say if y equals f of u is a differentiable function of u. So typically we're used to seeing f of x, where we have a function of x, but now we're seeing it in terms of u, and u equals g of x is a differentiable function of x. Then y equals f of g of x, so let's just stop there. This should make sense, right? Because y equals f of u and u equals this, so we're just plugging this into here, and we get f of g of x. So y equals f of g of x is a differentiable function of x, right? It's a function of x now, and the derivative of it, dy dx, remember that's our symbol for derivative, that is equal to dy du times du dx. So this means we take the derivative of y with respect to u, which makes sense because we're given y as a function of u. So you can think of this as something like y equals u squared plus u, right? When you take the derivative, you wouldn't say dy dx equals this. You would say dy du equals, in this case, 2u plus 1, because we're doing it with respect to u. So dy du times du dx, and that comes from here, right? U might equal 3x plus pi, right? U is a function of x. So we take the derivative of u with respect to x. Du dx in this case would be 3. And then the derivative of y with respect to x is the product of these two. That can be a little bit confusing. So typically we'll see the bottom part here, where the derivative of this composite function, f of g of x, is equal to f prime of g of x times g prime of x. So on the right here, I included some quotes that might help you remember it. So the chain rule, you're taking the derivative of the outside and multiplying it with the derivative of the inside. So we can kind of see that here, right? The outside is f of x, and the inside is g of x. So we take the derivative of the outside. That's why we have f prime. But the inside is still g of x. And then after we take the derivative of the outside, we multiply it by the derivative of the inside. And an important thing here is don't forget to de-stuff it. So stuff is just whatever is inside our function. It might be a little confusing as to what inside means, but we'll see it in an example. But so the stuff is what's inside, and then d means to take the derivative. So don't forget to de-stuff it. Take the derivative of the stuff. So yeah, it might be a little confusing, but let's clear it up with an example. So find the derivative of f of x equals x squared plus 1 to the power of 3. So this kind of looks like a power rule type of question, right? we might say that by the power rule, f prime of x equals, well, the power rule tells us to bring down the exponent, so that would be 3, and then we keep this term, and then we subtract the power by 1, 2. But this actually doesn't work. The power rule worked when we were dealing with x. Like if it was x cubed in this case, it would work. But since we're dealing with a function, I suppose, well, I mean, I guess x is a function itself, in this case, it doesn't actually work. So yeah, this is the wrong answer. Let me just cross it out. So we have to use the chain rule instead. So suppose we let let's look at this part here, x squared plus 1. Suppose we let h of x equal x squared plus 1, and g of, I guess, x equals x cubed. So then, if we were to take g of h of x, with g of x, we took whatever was inputted into it, x, and we cubed it. So if we're inputting a function, we should cube the function. So this would be equal to, I'm just going to rewrite this in a different color. So h of x, nope, that's too bright. H of x equals x squared plus 1. And then if we change this to the green color, h of x, this is equivalent to g of, let me just add this color down below. This is equivalent of saying g of x squared plus 1. And then I'll use the orange, I suppose, here. So I'm trying to use the colors to differentiate between the functions. And that, of course, I don't know why the color didn't save, that is equal to x squared plus 1. Okay, the color's not saving, but that's all right. That function to the power of 3. I want to use the orange for it. There. Right? And that is what we're looking at with f of x. So this is equal to f of x. Right, so that's a little bit complex, but now we've separated our f of x into two functions, and now we can use the chain rule from up above. So we know that d dx of, I'm going to use g's and h's because we have it in the form g of h of x. G of h of x, the derivative of this is equal to g prime of h of x times h prime of x. So we can solve for this, right? We have g of x, we have h of x. We just need to compute g prime and h prime, really. So if g of x equals x cubed, then by the power rule, g prime of x equals 3x squared. Similarly, if h of x equals x squared plus 1, this tells us that h prime of x, by the power rule, is 2x. So we have this right part here, h prime of x, but we still need this g prime of h of x. So g prime of h of x, that is taking a function, in this case we're taking h of x, and we're substituting it for x here. So this x should be this h of x function, which is x squared plus 1. So if I underline this in orange, g prime of h of x, and I'll underline this in red, this is equal to 3 times x squared plus 1, all of that squared. And therefore, g prime of h of x times h prime of x equals 3 times x squared plus 1 squared times 2x. And that would be our answer. So hopefully that made sense. But there's also a little bit of a quicker way to do it, using the idea of the derivative of the outside times the derivative of the inside. So if we let f of x equal x squared plus 1 cubed, which is what we had, what we're first going to do is, well, let's compute f prime of x. we start by taking the derivative of the outside. So we're going to treat this as just one term, just as if it was one variable, right? As if we could apply the power rule. So we will apply the power rule. This would be 3, and then we'll keep this, we won't have to worry about it, squared. That's just the normal power rule. But now we have to destuff this. So take the derivative of the stuff, multiply it with the derivative of x squared plus 1. And that will give us 3x squared plus 1 squared times 2x, which is what we got here. So that's the quicker approach to doing it. But I like the first approach when we're first learning it because it shows how the function decomposes into two separate functions. And yeah, so for the next one, it's a similar question. Let's try to do it. So find the derivative of f of x equals x squared times the square root of 1 minus x squared. Wow. Okay. So we might be thinking, okay, we need the chain rule because we just learned the chain rule. But really, we're dealing with a product of two functions, right? We're dealing with the product of x squared multiplied with the square root of 1 minus x squared. So we'll use the product rule, right? F prime of x, I'll just write it here, product rule. And this, if we remember from last week, is 1d2 plus 2d1. So what does that mean? We take the first term, multiply it with the derivative of the second term, and then we add the second term times the derivative of the first term. So this red term here, that's the first term, and this orange term here is the second term. So this is equal to 1x squared times the derivative of the square root of 1 minus x squared plus the second, which is 1 minus x squared, times the derivative of the first, right? X squared. Okay, whoops. All right. Some technical difficulties just for a moment. I'm going to take care of that, and we'll be back. All right. Yeah, accidentally turned off the iPad. But anyway, so we have the product rule, and it makes sense. And, well, this second term here, this d dx of x squared, we should know this pretty easily by now by the product rule. That just goes to 2x. But now we have to compute this term, which is not looking too great. So let's try it. d dx of the square root of 1 minus x squared. Well, we can rewrite the square root as a power, right? Because the square root is just something to the power of 1/2. So 1 minus x squared to the 1/2. And well, that kind of looks similar to what we just did up here, where we had some function raised to some power. And we used the chain rule. So that's what we're going to do. We're going to use the chain rule here. And I'm going to do it. Actually, I won't do it the quick way. I'll write it out. So let's let g of x equal x to the 1/2 and h of x equal 1 minus x squared. Then g of h of x equals 1 minus x squared to the 1/2. And you can try that out for yourself and see why that's the case, but essentially for g of x, I just took the outside part of it. The 1/2 power was on the outermost part, and then h of x is what I was applying that 1/2 power to, so I just let h of x be the inside, and we can see that it works out. So, by the chain rule, d dx of g of h of x equals g prime of h of x times h prime of x. So let me just switch colors here. I'll just go back to black. We can compute h prime pretty easily. H prime of x, we use the product, or not the product rule, the power rule. the derivative of 1 is 0, and then the derivative of negative x squared is negative 2x to the power of 1, because we decrease the power by 1. So h prime of x is negative 2x. And then g prime of x, I'll just write g of x here, so we have it close by. And this is just a simple power rule. We bring down the exponent, we keep the variable, and then we decrease the power by 1. So now we can apply g prime of h of x. So that would be this function here, where the x has this negative 2x substituted in it. So that would be equal to 1/2 times negative 2x to the negative 1/2. That's this g prime of h of x term here. Oh, sorry, that's actually not true. G prime of h of x is this, but the x term is 1 minus x squared, because that's actually h of x. So let me just erase this. 1 minus x squared. And now we multiply with h prime of x, which is negative 2x. So that is this derivative of this second term here of the first product. And now, quickly before we go back and substitute it back in, because we still have to simplify this product, let's just try computing the derivative of 1 minus x squared to the 1/2 using the chain rule, but the quicker way. So we ignore the inside part, which is the 1 minus x squared, and we take the derivative of the outside, which is that 1/2 power. So we use the power rule again. So 1/2, we don't touch the inside, we decrease the power by 1, and then we take the derivative of the inside, d dx of 1 minus x squared, and that's equal to 1/2 1 minus x squared to the negative 1/2 times negative 2x. And we can see that these are the same thing. But now we have to go back to this f prime of x and simplify. So we get f prime of x equals x squared times this huge behemoth of a thing, 1/2 1 minus x squared to the negative 1/2 times negative 2x, something like that. There might be an extra parentheses in there. That plus the second term, 1 minus x squared square root, times 2x. And that is our answer. Something like that. We can simplify it further if we wanted to. I don't feel like doing that because that's just a lot of algebra. But the point is we have calculated the derivative. It is that answer. Just not simplified all the way, but yeah. So that's a little bit of a more complex example. Hopefully now you're starting to realize how we can do the chain rule the quicker way. Derivative of the outside with the inside intact multiplied by the derivative of the inside. So with that said, of course we have to visit our trig functions. So we're taking the derivative of the trig functions with respect to u. Well, actually not with respect to u. We're doing it with respect to x, but the functions themselves are on u, where u is a function of x. Okay, so this would be like sine of f of x or something, tangent of f of x, but we're just representing that function of x with a u. And what we can see here is that it's very similar to what we've seen with the chain rule. Cosine of u, that would just be the derivative of sine of u, right? If u is an x, the derivative of sine of x is cosine of x. But since u is a function of x, we multiply it by the derivative of u prime, right? So that's the derivative of the outside. This is the outside. And we're multiplying it by the derivative of the inside. We're de-stuffing it. And we can see that holds through. Cosine goes to negative sine, and then we multiply by that inside term. Same thing here, here, there, and there. So these are helpful to know. All right, find the derivative of f of x equals cosine of 2x. Well, we just saw that the derivative with respect to x of cosine of u, where u is a function of x, equals negative sine of u times u prime. Well, if we let u equal 2 of x, or 2x, then f of x equals cosine of u. And really this would just be f of u because it's a function of u now, but let's not get into the semantics. And then, well, then the derivative of f of x equals the derivative of cosine of u, but we're taking the derivative with respect to x. And we know that this is equal to negative sine of u times u prime, and if u is 2x, then u prime equals 2. So then we just substitute negative sine of 2x times 2. And that's our answer. Simple as that. So we don't always have to show this u thing where we create this variable u and set it to something. We can still do the chain rule normally with our faster method, so I'll briefly show that. We have f of x equals cosine of 2x. So the outside is the cosine part, right? The cosine is being applied on this 2x, so this 2x is the inside part. So we do the derivative of the outside, which is negative sine. We keep the inside intact, and then we multiply it by the derivative of the inside. We de-stuff it, so we multiply it by 2. And we get the same answer. So yeah, we saw both ways of doing it. And yeah, definitely the faster way is, it's more conventionally done just because we do derivatives so often. So yeah, I would get in the habit of doing it this longer way, just so that way you're able to show your work very well. But once you've done enough practice and you feel confident in yourself, you can feel free to switch over to this faster way of doing it. Just don't forget to de-stuff the inside. Okay, so now we have f of x equals cosine squared of 2x. So this one's a little bit different, right? We just did cosine of 2x. Now we want to see what happens when we have cosine squared of 2x. And this kind of seems like a chain rule type thing. In fact, let me just rewrite this as cosine of 2x, all of that squared, right? So let's try to use this outside-inside type thing. So what would be the outside? In the last problem, the outside was the cosine, right? Because the cosine was being applied on the 2x. But even before that, now our outside is the squared term. Something is being squared. So let's take the derivative of the outside. Derivative of outside. Well, that's just a simple power rule, so we bring down the exponent, and then we multiply it with something, and then we decrease the power by 1. So what is that something we multiply it with? Well, that would be the inside, right? What is being squared? So that would be cosine of 2x. But now we have to multiply it by the derivative of the inside. So the derivative of inside, that is equal to the derivative of cosine of 2x. And well, that looks like a chain rule problem, but we kind of just solved that in the previous problem here, and we said it was a negative sine of 2x times 2. So this, I'll just rewrite it as negative 2 times sine of 2x. And now we'll do our derivative of the outside times the derivative of the inside type thing, and we get that f prime of x equals 2 times cosine of 2x to the power of 1 times negative 2 sine of 2x, right? So that's just the normal outside-inside type thing. And then we can simplify this a little bit more, saying negative 4 sine of 2x cosine of 2x, right? And it's as simple as that. So now we've sort of used this outside-inside thing a little bit more. So hopefully you're getting familiar with it. Alright, so here's a nice picture that summarizes a lot of the differentiation rules we have learned thus far. So I'll briefly go over the few. So f, g, and u are functions of x. They're differentiable functions of x. So if we have a constant times a function of f, the constant isn't affected by this differentiation. We can like sort of bring it out. So this is the same thing as saying c times d dx of f, and the proof of that is simply in the power, or not the power rule, the product rule, right? If we were to do the product rule on this c times f, we would get c times the derivative of f plus f times the derivative of c, but the derivative of a constant is 0, so the second term goes to 0, so we're just left with c times the derivative of f, which is cf prime. And then for when we are adding or subtracting two functions, the derivative just carries through. So we do the derivative to each individual function, and then we add or subtract them as normally. The product rule I just mentioned, that's 1d2 plus 2d1. That's the trick to help you remember that. Then we have the quotient rule, which is when we're dividing two functions. And the trick for that is low d high minus high d low all over low low. So in this case, low is g, high is f. So low d high is the derivative of f, minus high d low is the derivative of g, all over low low, which is low times low g squared. Cool. We mentioned the derivative of a constant is 0. We've seen the power rule, where we have x to the power of n. You drop down the exponent to the front, and then you keep your x term, and then you decrease your power by 1. And then that's generalized here when n is 1. In this case, x to the power of 1 would be 1 times x to the 1 minus 1, so 1 times x to the 0, which is just 1. That's that. Here we have our trig functions, which hopefully you're starting to memorize. At least know sine and cosine. Those are really important, because in case you forget these last four, you can derive them using the quotient rule, because most of these are just quotients. Tangent is sine over cosine, secant is 1 over cosine, cotangent is cosine over sine, cosecant is 1 over sine, and then just use the quotient rule. Then the chain rule is just what we did. If we have f of some function of x, it's the derivative of the outside times the derivative of the inside. And then we have a general power rule here. So this is sort of what we saw with that example, x squared plus 1 all to the power of 3, where we dropped down the power, we kept that inside function, decreased the power by 1, and then de-stuffed the inside. And if this doesn't make sense, you can go back to that example I just did, and then compare that answer with this formula, and you'll see the relation between the two. So as you can see, we've learned a lot about differentiation. Now it's just a matter of learning when to use which. So let's do a little bit of practice. Find the derivative of f of t equals that. Okay, so there's a couple things you can do here. First thing you might be thinking is maybe we need a quotient rule at some point because it looks like a quotient, and maybe we will. But maybe you recognize that we have a large quantity, a function of t being squared. So maybe you're thinking, okay, let's take this and just multiply it by itself, and then maybe that'll give it in a better form and we'll be able to reduce it. And yeah, we can very well do that. And lastly, you might realize that, oh, okay, that part that I just blocked out, that's a function of t, and it's being raised to the second power, so maybe we can use the chain rule that we just did. So let's do that, because we haven't done much with the chain rule. So let's try to do it the quick way. So f prime of t. We start by doing the derivative of the outside, which is the exponent part. So we bring down the exponent. This is just the power rule type thing. And in fact, we're going to be following this thing up here. So in this case, n is 2. So we bring that down. U is the function of t in this case. So this inside part stays the same. And then the power n minus 1 would go to 1. And then we multiply this by the derivative with respect to t of t squared over t cubed plus 2. Right? So now we have to figure out, well, what is this derivative? d dt of t squared over t cubed plus 2. Well, now it really seems like we need the quotient rule, right? Now we really need it. So we're going to use our low d high minus high d low all over low low. So low is t cubed plus 2 times the derivative of high, d dt of t squared, minus high times the derivative of low, t cubed plus 2. Right? And we're dividing all of that by low low, which is t cubed plus 2 squared. So let's simplify the numerator. T cubed plus 2, derivative of t squared, that's just the power rule. Drop down the power, and then lower the exponent by 1, minus t squared times the derivative of t cubed plus 2. So the derivative distributes to each. Derivative of t cubed, power rule again, that's 3t squared. Drop down the exponent, keep the t, lower the exponent by 1. And then derivative of 2 is just 0, so we add 0. And we divide that all by t cubed plus 2 quantity squared. Right? Okay. And then what can we do from there? Well, we can simplify it if we want to, but I don't really feel like doing that. So we'll just say that f prime of t equals 2 times t squared over t cubed plus 2 times this huge thing, t cubed plus 2 times 2t minus t squared times 3t squared. All of this over t cubed plus 2 squared. And I believe if you do feel like simplifying this down, this should go down to something like 8t cubed minus 2t to the 6th. All of that over t cubed plus 2 cubed. Something along those lines. Whoops. Right, so that's going to be our answer. Now, another way of doing this is you can say that, well, okay, f of t equals t squared over t cubed plus 2 squared. Well, I know that that's equal to t cubed, this term, multiplied by itself, right? And I'm pretty good at multiplying fractions. That's equal to t to the power 4 over t to the 6th plus 4t cubed plus 4. Then I'm like, hey, wait a second. Now I can just use the quotient rule. And you can. Yeah, feel free to do that. This totally works. We just manipulated what we started with into a form that's maybe a little bit easier. And then you just use the quotient rule like normal, and you should get up with the same answer, I hope. So sometimes that works, where you can just do a simple trick and use a different technique. But if this power up here was like 5, and I wouldn't want to spend that time multiplying out all of those fractions and then hoping that I don't mess up my algebra. For that, I would want to use this chain rule. Awesome. So that's a good question. Next, find the derivative of 5 sine squared of pi x. Okay, so I'm just going to rewrite this because the convention for writing sine squared is just not very fun for me. It's like that. Okay? So, if we remember, well, 5 is a constant, right? So the derivative of 5 times sine of pi x squared, we should remember that the constant just comes out. I explained that just a moment ago. And so now we want to find this sine of pi x squared. So how are we going to do that? Well, hopefully you've been able to guess it by now. That's a job for the chain rule, right? And we'll do our outside-inside trick. So the outside part is the squared part, right? The squared is being applied on some function. So we do the power rule, 2 times, we keep the inside, sine pi of x, and then we decrease the exponent by 1, and that we multiply with the derivative of the inside. Okay? So that is equal to 2 sine of pi x. Well, then what's the derivative of sine of pi x? Well, we know that that is equal to, well, that kind of looks like the job for another chain rule. So I'm just going to leave this blank for a moment, and let's compute that. Sine of pi x. Right? If it was sine of x, we know how to do that, but now it's being multiplied by something. So again, what's the outside function? The outside is the sign. Sign is being applied on something. And it's being applied on pi x, which is also a function of x. So the inside is pi x, the outside is sine. So the derivative of the outside is cosine. We keep the inside intact. And then we multiply that by the derivative of the inside, right? And well, that should be pretty easy to see, that the derivative of pi x is just pi. The derivative of c times x is c, where c is a constant. So that's that. So now we can put this back in here. And I'll use a different color for that, times cosine pi x times pi. And then that tells us that our answer is f prime of x equals 5. Don't forget this 5 up here that we factored out. We still need that. 5 times 2 sine of pi x times cosine of pi x times pi. And that we can just simplify 10 pi sine pi x times cosine of pi x. That's our answer. So yeah, that one's a fun one. It's the first time I think we really threw pi into something and we did a lot of pi work. Yeah. If you haven't tried memorizing digits of pi, you should try doing it. It's fun. I tried getting some of my friends to do it, and well, they lost interest pretty quickly, but I tried continuing it, but stopped memorizing after a couple of years. But anyways, that's a story for another time. Now we move on to a new section. So we've explored a lot of techniques for integration. I think that was the entire, not integration, for derivatives. That was the entire section 2, all of those techniques. So now we move on to something called implicit differentiation, which it's not a technique for differentiation, or it's not a trick, it's a specific instance in which we need to use a special kind of differentiation. So whereas the previous things we went over were tricks, this is a specific type of differentiation. And to make that clear, we will define it now. So let's first discuss what are implicit functions. So right now, or up till now, we've been taking derivatives of functions in the form of y equals f of x, or y, or we have just some function of x, right? So y is x plus 2 or sine x, and we can easily take those derivatives, right? The derivative of this one, dy dx, is 1. The second one, dy dx, is cosine of x. We're used to doing that. And these are called explicit functions. Now we deal with the implicit functions, and these are functions in which y can't be isolated as nicely. Or rather, y is just not isolated. So certain implicit functions, such as this one right here, xy equals 1, we can rearrange it to get an explicit form, y equals 1 over x. We just divide both sides by x, pretty simple. But if we have something like this, where y isn't isolated, how do we isolate y there? That just doesn't seem very easy to do. But this is still a very valid function. We can graph that and see what it looks like. But as of right now, we wouldn't know how to take the derivative of that. So that's where implicit differentiation comes in handy. And we're going to do this to take the derivative of implicit functions. So let's see what goes on with this. So we've discussed this dy dx term multiple times, right? We said that that was just a way of notating that we're taking the derivative of something. So, and we've been using this vocabulary that we're taking the derivative of a function with respect to x. With respect to x. Why am I giving respect to a letter? That makes no sense. Come on, this is math. Respecting letters. Yeah, no. That's just the terminology we use. And it means that when we're differentiating terms involving x alone, we differentiate as usual. So with the previous examples where y equals x plus 2, when we take the derivative of that, x is alone and we just differentiate as usual. But when we differentiate terms involving y, like this example up here, when that happens, we have to apply the chain rule since we're making the assumption that y is defined implicitly as a differentiable function of x. So what does that mean? That means up here, when we take the derivative of this, which we will be doing, we're going to use the chain rule. So in this case here, 2y squared, we can think like the outside part is the squared part, and the inside is the y part. We'll forget the coefficient of 2, but that's how we're going to start to be thinking. We're not going to think of that as just like x squared and the derivative is 2 times x. No, this is, when we see a y in this form, we want to think chain rule. Outside times the derivative of the inside. Yeah, d outside times d inside. So it seems a little bit confusing, but it'll make sense shortly, at least I hope. So let's take a look at an example here. So if f of x equals x cubed, and we want the derivative of that with respect to x, the variables agree. So we can take the derivative as normal, and that's why we use the power rule, 3x squared. Drop down the power, keep the x, decrease power by 1. Now we want to take the derivative with respect to x of this y cubed term. The variables do not agree here. Different variables. So we can't differentiate like normal, but we will use the chain rule, and we'll think about it like outside inside. So the outside is this cubed term and the inside is this y term. So if we do the derivative of the outside, we bring down the power with just the power rule, 3, we keep the inside y, decrease the power by 1 squared. So that's what that's saying up here, nu to the n minus 1. That's just the power rule, that's the outside. And we multiply it by the derivative of the inside. So the derivative of y with respect to x is dy dx. That's literally what it means, the derivative of y with respect to x. So this requires the chain rule. This looks very familiar here, right? That's just this, except with a y. But we have to multiply it by this dy dx term, just because the variables don't agree there. So let's see another example here. The derivative with respect to x of x plus 3y. So the derivative distributes, so it's the derivative of that plus the derivative of that. So d dx of x, the variables agree, so we take the derivative as normal. Derivative of x is 1, and then the derivative of 3y, mess that up, well, we can use the product rule, or we can just think that the coefficient comes out, so it would be 3 times the derivative of y, so 3 times dy dx. So that's why that's there. Finally, we have this example, and that looks like a product rule, x times y squared. So 1 d2 plus 2 d1, right? And this second one, that's easy to do. Derivative of x with respect to x is 1. That's why that's there. Derivative of x with respect to, or derivative of y squared with respect to x, well, we do power rule. Well, we do the chain rule, but first, in order to implement the chain rule, we do the power rule on y, so that becomes 2y, and then we de-stuff it. We take the derivative of the inside, which is dy dx. And then we just simplify that down, and we get the bottom part. All right, so hopefully it's starting to clear up. The main thing is when we see a y and we're taking the derivative of it with respect to x, that usually means we need to throw in a dy dx term in. We just need to do it correctly. So here's some steps for implicit differentiation. So differentiate both sides of the equation with respect to x, then isolate all terms involving dy dx onto one side of the equation, and keep all non-dy dx terms on the other side of the equation. Then factor the dy dx term and solve for dy dx. So what does that mean? Well, if we take the derivative of some function, or if we're given some function, and we're trying to solve for the derivative, dy dx, well, we have this, but we don't have dy dx as a function of the other variable. So we have to solve for this variable. We'll see it in an example shortly. That is so difficult to say. And speaking of the example, we're asked to find dy dx, given that we have this equation right here. So, what are some things we know about math? Well, hopefully a lot of stuff, and that's a pretty broad question. but one of the most important things about math is you can usually do the same thing to both sides of the equation, right? If you want to add 2 to this side of the equation, you got to add 2 on that side of the equation. That's just how math works. Can't always do stuff like that, when you can't always just multiply both sides by 0 or divide both sides by 0. You run into some issues. But this is like a major tenet of math, where you just do stuff on both sides. So, similarly, by that logic, I can take the derivative of both sides, right? Because if we say that this is equal to this, then they're basically the same function. So when I take their derivatives, they should be equal, right? So let's do it. dx, we're taking it with respect to x, of y cubed plus y squared minus 5y minus x squared equals d dx of negative 4. Well, what's d dx of negative 4? That's equal to 0. So now let's figure out what is this d dx of this top term here. Well, remember when we're adding and subtracting stuff, the derivative just carries through. So it's d dx of that term plus d dx of y squared minus d dx of 5y minus d dx of x squared, right? And that equals 0. Okay, so let's do d dx of y cubed. As we just saw previously, we treat y as if it were x, right? Or that would be the first step in doing the chain rule, because when we're taking the derivative when the variables don't match, we think chain rule. So the derivative of the outside would be 3 times something squared, but that something is the inside, which is y squared, and then we have to de-stuff it. So we multiply it by dy dx. Similarly, the second term follows a very similar logic. Power rule, de-stuff. This third term here, this is just a constant times y. So this is 5 times the derivative with respect to x of y. So that's just simply dy dx. And lastly, we have d dx of x squared. Well, now the variables match, so we just do the normal differentiation. So that's just 2x, and that equals 0. But we're asked to find dy dx, and we haven't yet done that. So we have 3 terms with dy dx in them, and 1 term without it. So let's isolate the dy dx terms. This is step 2 here. So this tells us that 3y squared times dy dx plus 2y times dy dx minus 5 times dy dx equals 2x, just by adding on both sides. And then we can factor out a dy dx because it's common to all 3 terms on the left-hand side, and we get this polynomial. That's equal to 2x. And finally, well, we can just simply divide by that polynomial, and we get dy dx equals this. And you might be a little confused as to why is there y terms in our dy dx. Well, it's fine. It's totally fine. Remember, it's just the measure of the slope of the tangent line at a specific point, right? So as long as we have that x and y coordinate, we can compute dy dx, right? It's the first time we've really seen y's in this form, but it's totally valuable. Like, it's totally fine. If I tell you what's the slope of the tangent line at the point, well, I don't know what point is on it. I guess 2, 0, because that would be on it. 0 cubed plus 0 squared minus 5 times 0 minus 2 squared equals negative 4. Well, you just plug in 2 for x and 0 for y, and you'll get negative 4/5. It's totally fine. All right. Ooh, this one. Given x squared plus y squared equals 25, find d squared y dx squared. So that's the second derivative. And, well, it's not that hard. So this is equal to the derivative of dy dx, right? We find the first derivative, and then we take the second derivative. So yeah, that's just a different way of writing it. So let's find that first derivative. So we'll do the same thing where we take the derivative of both sides, because that's something we can do. And, well, what happens here? This tells us that the derivative with respect to x of x squared plus derivative with respect to y, or with respect to x of y squared, equals derivative of 25. Okay? So d dx of x squared, variables match, normal differentiation, power rule 2x, plus d dx of y squared, variables don't match, we think chain rule. Derivative of the outside, use the power rule, 2y to the power of 1 times derivative of inside, we got to de-stuff it, dy dx. That equals derivative of 25 is 0. Man, if you say the word derivative over and over again, it gets really difficult, but okay, we continue. I'm going to erase this 1 here because it looks like a prime, but it's not a prime. And now we can just solve for dy dx. So 2y times dy dx equals negative 2x. And that tells us that dy dx equals negative 2x over 2y, which is equal to negative x over y. Cool. But we want d squared y dx squared. So we have to take the derivative of that again. So now we're curious as to what is d dx of negative x over y. Well, that looks like quotient rule. So let's use the quotient rule. I'm just going to rewrite this as negative x over y. So the negative is in the numerator, just so we have a term to group it with. So what's the quotient rule? Low times the derivative of high minus high times the derivative of low, all over low, which is y squared. So y times derivative of negative x with respect to x, variables match. We do it like normal, that's just negative 1, minus negative x. d dx of y, variables don't match. So we should know that that is just equal to dy dx, right? That's sort of our definition. And we multiply that, or we divide that rather, by y squared. Okay? And this is equal to d squared x, or rather, d squared y dx squared, right? Okay, so let's simplify it a little bit. dy squared dx, d squared y dx squared equals negative y plus x times dy dx over y squared. And you might think that we're done and we're so close to being done, but this is something that I always forgot to do. This dy dx, we've already computed that to be negative x over y, so we have to substitute that in. So this is negative x plus, or negative y times, negative y plus x times negative x over y, so many variables, all over y squared. We can simplify that a little bit further. Negative y minus x squared over y, all of this over y squared, and that should be equal to something along those lines, I hope. Let me just make sure. Almost. In fact, this is basically the correct answer. But we can simplify it even further, believe it or not. This is equal to negative x squared plus y squared, all of this over y cubed. And you might think that's not much of a simplification, but in fact it is, because we are given x squared plus y squared equals 25. What an insane substitution that we have to make. How do you even remember to do that? Well, you just got to be really careful. And now we have found our second derivative. Unbelievable stuff right there. Yeah, really, this answer up here, even though it seems okay, it's correct, but we really want to be as correct as possible. So we want to make those substitutions. We want d squared y dx squared in terms of x and y only. And it just so happens here that we had this insane substitution. So yeah, just got to be careful with those substitutions. Awesome. Okay. Now we have a question that tells us specifically to use implicit differentiation. So that's pretty exciting. So we want to find an equation of the tangent line, so that, that's differentiation right there, to the ellipse that at a point. Cool. So what do we need to find here? This is telling us dy dx equals question mark. Well, we seem to be pretty good at derivatives at this point, that we can find this derivative pretty easily, I hope. So I'm going to rewrite this a little bit differently. This is 1/2 x squared plus 1/8 y squared equals 1. And we know that we can take the derivative of both sides. And in fact, I'm just going to save us one step and just distribute this derivative. And that equals the derivative of 1. Well, we know derivative of 1 is 0, and then I'm just going to bring out this constant here just to, really remind us of that fact. Hopefully this fact where you can pull out the constant is getting ingrained in your memory, because in the future I'm just gonna do the differentiation straight. So we're not gonna say that, oh, this term here that goes to 1/2 times 2x. In the future I expect you to be like, okay, derivative of 1/2 x squared, that's just x. It'll be 1/2 times 2 times x to the power of 1. But for now, since we're still getting started with derivatives, I will take the time to write it out. And this is 1/8 times, well, now we have to be careful, d dx of y squared. Variables don't match. What are we thinking? Chain rule, implicit differentiation. We need a dy dx term. So what's the outside? The outside is the squared part. So we do power rule. 2y, and we reduce the power by 1, so that becomes 2 minus 1, which is 1. And then we have to destuff it. So we have to multiply by the inside, the derivative of the inside. So the derivative of y with respect to x is dy dx. That equals 0. So we simplify this a little bit, and we get this. That equals 0. And that tells us 1/4 y times dy dx equals negative x. And now we can solve for dy dx, right? Just multiply both sides by 4 over y, and we get negative 4x over y. Okay. So now we are given a point. We want to find the tangent line at that point. So dy dx at 1, 2 equals negative 4 times 1, all of this over 2. That's just negative 4 over 2, and that is negative 2. Right? And just for fun, let's see, what does this ellipse really look like? So if you're unfamiliar with drawing ellipses, that's okay. It's been a while since I've graphed an ellipse, but we have an x-intercept at the square root of 2. So that's somewhere here. We have a y-intercept at the square root of 8, which is a little higher. Also the negative counterpoints. And it should look something like that. Thank you for adjusting that. All right. And then the question is asking, what is the slope at 1, 2? Well, 1, 2 is somewhere there. And then the tangent line is something like this. It's not a great tangent line, but you can really see that, okay, the slope is definitely negative. And if you told me that the slope was negative 2, I'd be like, yeah, sure, why not? That looks negative 2 enough to me to believe it. So yeah, you should be feeling pretty confident with your answer. Cool. So that is implicit differentiation. I really loved implicit differentiation when I learned it, because you have to be like extra careful with the y, and then you have to do a little bit more algebra to solve for dy dx. I enjoyed that, but everyone has their own preferences. So now we moved on to section 4, which is related rates. And this is a pretty important section, I think. We're really going to be applying derivatives in a way where we can solve real world problems. So up till now, we've sort of just been saying, here's a function, what's the derivative, what's the slope of the tangent line? I don't really care that much what the tangent line looks like. Hopefully you're not saying that. Hopefully you see the excitement in this. But now we're going to see some potential real world applications. So here's what we're going to do. We need to use implicit differentiation to find dv dt if v equals pi over 3 r squared h. So we're going to start out with a problem, and then we'll get more into it. So this equation for v is in fact the volume of a cone, 1/3 pi r squared h. Hopefully you're familiar with that. So suppose we have a conical tank filled with water. This problem is essentially asking us, what is the change in volume of the water with respect to time? Okay, so we have this conical tank, and we're seeing what's happening to the water as, time passes. Okay, so let's see what's going on here. But it might not make too much sense right now, the answer that we get, but it'll be explained shortly. But let's just use what we know to see what kind of progress we can make. So we want dv dt. dv dt equals question mark. And we have v equals pi over 3 r squared times h. Okay, well, let's just try to take the derivative of this. dv dt equals d dt, we're differentiating with respect to t, of pi over 3 r squared h, right? So that is equal to pi over 3 times d dt of r squared times h, right? We're just pulling out that constant. And well, this really seems like we need the product rule. So let's do that. That's equal to pi over 3 times 1 d2 plus 2 d1. So 1 times d2, so remember, respect to t, plus 2 times the derivative of the first with respect to t. Okay, so what is d dt of h? Well, that's very similar to dx of y, right? It's just two different variables, and the point is that the variables don't match, so we have to do that implicit differentiation. So that's just dh dt. Similarly, if we ask what is d dt of r squared, that's like me asking what is d dx of y squared, right? We do a similar technique where we do this power rule type thing, 2r times d dt, and we're differentiating r with respect to t. It's very similar to what we just did, except now with different variables. So now we just substitute pi over 3 r squared times dh dt plus h times 2r times dr dt. And really, that's what we're going to keep the answer at for now. And you might be like, okay, what does this even mean? I thought you said this was going to be a real-world application, but right now I have a bunch of pi's and r's and h's and t's, and the only numbers I see are 2's and 3's, so you're like, is this even math at this point? Or is this English? Stick with it. We will see very shortly that this is going to have some really cool usages. We'll be able to determine a lot of interesting stuff, but let's first clarify what's going on with related rates. So, from the previous problem, the one we just did, we were tasked with finding dv dt. And the answer we obtained was in terms of dh dt and dr dt, right? This is the answer we got. But we didn't know what to do with this and this, right? That's just, I don't know what to do with that. So, let's see. We know that the derivative is a measure of the rate of change. So this is telling us the rate of change of the volume with respect to time. Suppose we're adding water to this conical tank or subtracting water from this conical tank. The rate of change of that volume of water depends on both the height of the tank and the radius of the tank, right? R is radius, H is height from that formula 1/3 pi r h squared. pi r squared h, right? And that should kind of make sense if you think about it. If you have a really, really tall tank that has a small radius, the way water enters or exits that is going to be different than if we had a really wide tank that wasn't very tall. So it should make a little bit of sense. Your intuition should be saying, yeah, I'd believe that, right? It does depend on these two factors. So that's what's going on there. So let's see if we can work through a problem. I know we don't have too much to go on, but we're going to try to learn how to do related rates by going through a problem. So a pebble is dropped into a pond, causing ripples in the shape of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? There's a typo there, but that's okay. All right. So we're working with circles, we're working with area, and we're given something about radius. So a logical first step is to find some sort of equation that links some of these topics. And the first thing I think about is A equals pi r squared, right? The area of a circle is pi times the radius squared. We've given everything, we've given all three of these quantities, we're given that to us, and now we just created that equation. And we know that equation. Now, what else are we given? The outer ripple, the radius of it, is increasing at a constant rate of 1 foot per second. So something is changing with a certain rate that's given to us. And what do we know about rates? Well, derivatives are a measure of rates. So the derivative of something equals 1 foot per second, right? And if we look at the units, we might be able to guess what we're taking the derivative of, but it should also be intuitive from the problem. The rate of change of the radius is 1 foot per second. Second is a measure of time. So now if we read this out loud, the rate of change of radius with respect to time is 1 foot per second. That should make sense, right? And what are we tasked with finding? We want to find at what rate is the total area A changing at radius equals 4 feet. So at r equals 4, what is dA dt, right? The derivative of the area with respect to time, the rate of change of area with respect to time. We're just changing this rate of change to derivatives, right? So that's what we're tasked with finding, and we can do this. And the reason we can do this is, well, we created this equation here. So let's take the derivative with respect to time of both sides of the equation. Okay? So that gives us, the left-hand side is simply dA dt. The right-hand side, well, the pi comes out, and then we're just left with d dt of r squared. And then that tells us that dA dt equals pi times, well, we should be getting the hang of this now, power rule type thing. So 2r, then we multiply by the derivative of r with respect to time. You know, that's the chain rule, destuffing. And now we have this equation. So now we can solve for dA dt. dA dt equals pi times 2r times dr dt. And now we can find what is dA dt when the radius equals 4. That's equal to pi times 2 times 4 times 1 foot per second, right? So that's 8 pi. And we also have to have our correct units. Area is measured in feet squared, and we're measuring it with respect to time, which is in seconds. And that's our answer. So the next time you go to a pond and you throw a pebble into the pond as I always do and as most people always do, I encourage you to be that nerd and measure how fast are the ripples increasing, how fast is the radius increasing, and then see if this makes sense. Is the total area changing by about 8 pi when the radius is 4 feet? And maybe that makes sense. Let me see if I can think of an example here. Uh, here's one way of thinking about it, right? So let's say the ripple has the radius of 4 feet, and let's just look 1 second before it, when the radius is 3 feet, and 1 second after it. Oh wow, why is that terrible? 1 second after it, right? So the circles aren't completely concentric, but this is 3, this is 5, and this is 4, right? So at t equals, well, when the radius is 3, when r equals 3, the area is simply 9 pi, pi r squared. And then similarly, when r equals 4, area equals 16 pi. And then when r equals 5, area equals 25 pi. I don't know why I just switched colors there. But we can see from here to here, the difference is 7 pi. And from here to here, the difference is 9 pi. So you can sort of start to see that, okay, at that instance, right when we're at 4 pi, the rate of change is 8 pi. Because the rate of change is growing over time. As the circles get larger, you expect as time passes, the area would get larger, as it should. So it just so happens that 8 pi is the middle of 7 pi and 9 pi that we just got here. That's not always the case, it just happened to be that way. But this should give you some reason to believe that our answer is correct, right? It makes sense. Cool. Let's move onwards. So now I'll give you some steps for related rate problems. Feel free to write these down, take notes of it, remember them. So you want to identify and list the quantities given as well as the wanted quantities. And sometimes it's a good idea to sketch the problem because usually these are real world problems. You can, draw a picture. That always helps. Next, develop an equation that relates all of the variables given, or perhaps their rate of change has been given. So if you're given that, like previously, the radius has a constant rate of 1 foot per second, there we started to think that, okay, we need radius. That's how we came up with this equation. Then use implicit differentiation and the chain rule to differentiate both sides. Usually it's respect to t. Usually we're asking like, how is this changing with respect to time? But it really depends on the problem. So, don't always do t. It just, the majority of the time it is t. Then finally, after you solve for the derivative, make sure you're solving for the derivative. You can substitute the values that you're given, and then you just finish simplifying. So let's do another problem. And we can see that, okay, we have a rocket ship, so it's getting exciting. So a camera at ground level is filming a rocket that is rising vertically according to the position equation, s equals 50t squared. The camera is 2,000 feet from the launch point. Find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. Whoa, okay. So, what are some things we're given? We're given a position function. We're given, I guess, like a distance that the camera is. Distance. We're given a time, 10 seconds, and we want to find the angle of elevation. And if we use this picture given to us, that angle is theta, right? So I'll use red for this. Theta is what's really important here. So now we have to think, okay, how can we combine what we're given into one equation? Okay, so what is going on here? Well, we're curious, what is the angle of elevation at 10 seconds? So at t equals 10 seconds, what is the position of the rocket? Well, s of 10 equals 50 times 10 squared. That's just equal to 5,000, right? Simple as that. So now we want to find d theta dt, right? Because we're looking for the rate of change of the angle of elevation. D theta dt, when t equals 10 and s equals 5,000. But I guess that's sort of implied by t equals 10. Okay, so, well, we're given here that this is s. And we know this is 2,000. And we have this angle theta. So let's create an equation. Tangent of theta, that is equal to s over 2,000. Right? That's just the normal property of trigonometry. Right? Opposite over adjacent. So we have an equation. Let's take the derivative of it and see what happens. So d, what are we taking it with respect to? We're taking it with respect to time. Remember, we want that dt. So d dt of tangent of theta equals d dt of s over 2,000. Right? So the right-hand side is pretty simple. We take out this 1 over 2,000 term, and then d dt of s, that's just ds dt. Right? And then we're left with d dt of tangent of theta. So we do the outside function. Remember, if we think chain rule because the variables don't match, so the outside function is tangent. So the derivative of tangent is secant squared. And then the inside stays. And then we de-stuff it. We take the derivative of the inside, which is d theta dt. Okay, so that is the derivative of both sides. And we want d theta dt, so let's isolate d theta dt. That is equal to 1 over 2,000 times 1 over secant squared theta times ds dt. Okay, so, well, what do we do with that? Well, 1 over secant squared theta, that's 1 over cosine squared theta, because secant squared is 1 over cosine squared, so 1 over cosine squared is just cosine squared. So we can just write that out. D theta dt equals 1 over 2,000 times cosine squared theta times ds dt. Cool. So let's see. What is ds dt? S of t equals 50 t squared. So that tells us that ds dt, well, s is a function of t, so we just differentiate like normal. That's 100t. So that's taken care of. But now we have this cosine squared theta term here, right? We don't have a value for theta, but we do have a triangle to work with. Cosine of theta equals adjacent over hypotenuse, right? So what's the adjacent? 2,000. And what is the hypotenuse? Well, the opposite is s, and the adjacent is 2,000, so we use the Pythagorean Theorem, and we should get that this is c, so c squared equals s squared plus 2,000 squared. So c equals the square root of s squared plus 2,000 squared, right? Oops. Something like that. Right? That's just Pythagorean Theorem. So we plug that into here. 2,000 squared. And now we can substitute that back in. So we have now d theta dt equals 1 over 2,000 times 2,000 over square root of s squared plus 2,000 that quantity squared times ds dt is 100t, right? And now we can solve for d theta dt when t equals 10. So now we plug in t equals 10. I'm just going to rewrite this. Well, actually, we also have to plug in s, and we know that s is 5,000. So that's bad handwriting. 5,000 squared plus 2,000 squared, square root, that quantity squared, times 100 times 10. And that, did I compute it out? Yes, this should equal 2 over 29 radians per second, right? Because degrees are measured, angle is measured in radians. So there you go. Now we like to think, does this answer make sense? Yeah, maybe, right? You're 2,000 feet away from a rocket launch, and you're tracking the rocket. So your camera will tilt upwards very slowly until it gets like high enough. You know, it'll take time for it to track the rocket such that it's made a substantial change in the angle of elevation because you're so far away, right? Think about it. If you were watching a rocket launch with your own eyes, your head doesn't move up like all of a sudden super quickly. No, it'll take some time because you're so far away. And 2 over 29 radians is quite a small amount. I don't know the exact, maybe like 4 degrees, something like that. Yeah, something like that. I think 4 degrees per second. So, yeah, there we go. That's another real world application, another grouping of words that's very difficult to say. Okay, all edges of a cube are expanding at a rate of 6 centimeters per second. So we got some metric system stuff. How fast is the volume changing when each edge is 2 centimeters? Okay, so we have keywords or volume, cube, edges. So we should start to think at first, can we think of an equation? Maybe, but first let's figure out what are we trying to solve for. We're asked to find how fast is the volume changing. So we're looking at the rate of change of volume. So dv dt, based with respect to time, that's question mark. When each edge, I'll just say let S be an edge, and all edges are the same because it's a cube, when S equals 2 cm. And we're also given that the edges expand at a rate of 6 centimeters per second. So something equals 6 centimeters per second. Well, that is a rate of something, and in particular, the rate of the change of the edges, so ds, with respect to time. So now we can think about our equation. What's an equation that relates everything? Well, v equals s cubed, right? The volume of the cube is simply the cube of its side length. So let's take the derivative of both sides. d dt of v equals d dt of s cubed. And that tells us dv dt equals 3s squared times ds dt. So I kind of did some chain rule implicit differentiation really quick there. But the thing is, we realized that the variables don't match, so that tells us implicit differentiation. So to differentiate that, we use the chain rule. We bring down the 3 here, power rule, 3s, then we lower the exponent by 1, and then we destuff the inside ds dt. Hopefully you're starting to get the hang of it. And well, now we can just solve for dv dt. We have s and we have ds dt. So dv dt at s equal 2, dv dt equals 3 times 2 squared times 6. And that's equal to 3 times 4 times 6, and that is equal to 72 centimeters cubed per second. And there we go. So after the last one was quite intense, we got a little bit of an easier one here. But now we got another difficult one. But this one's interesting, I think. So a trough, it's a trough, right? That's how you pronounce it? Yeah, a trough is 12 feet long and 3 feet across the top, ends are isosceles triangles with altitudes 3 feet. Water is being pumped into the trough. Trough? Is it trough or trough? Bear with me. Whatever the correct pronunciation is, I apologize. At 2 cubic feet per minute, how fast is the water level rising when the depth h is 1 foot? Wow. Okay. So, first of all, we should really be thinking, what are we trying to solve for? We're trying to solve for the water level and seeing how fast it's changing. So we're thinking rate of change for the water level. And, well, we're given that the water level has depth h, so we'll use the variable h to represent our water level. So we want dh dt, that's what we're trying to find, when h equals 1 foot. And we're also given that water is being pumped into the apparatus at 2 cubic feet per minute. So that's a measure of the rate of change of volume, the volume of water. So we're given dV dt equals 2 feet cubed per second, right? And then we're also given some dimensions for this apparatus. I really don't want to say the name of it anymore because I don't know how to pronounce it. It's kind of embarrassing. Okay, so we should try to find the volume. But the volume of what? We can easily find the volume of the trough. Okay, I'm not saying it. But is that what we really care to find? Not really. Because we're given the rate of change of the volume of water with respect to time. So really, we want to find the volume of water. But the thing is, the water is changing. And as we can see in the diagram, in this case, the volume of water depends on this h. And that's okay. Just as in previous problems, where we had to use an equation where the area of a circle is pi r squared. The area, we didn't know what it was, but it depended on r. This is a very similar thing, so it'll probably depend on this h. So, how are we going to find the volume of the water? Well, we know that this apparatus is a triangular prism, right? We have a triangle here, and then a triangle on the other side, and then we have these parallel lines connecting it. It's a triangular prism. So the water fills the shape of that container. So the water forms a triangular prism. Triangular prism. So what's the volume of a triangular prism? Well, the volume of any prism is the area of the base times the height. Now, in this case, the base is the triangle, and the height is that. So I don't want to use this variable h because it's already being used for something. But yeah, and it should make sense, right? We take this variable, or this area, and then we just see how long it extends upwards, and we take that area. Okay, so, well, we know that the area of the base is a triangle, right? So area of base is a triangle, and the formula for that is 1/2 base times height. So I'm just going to take this, this triangle here and just sort of redraw it so we're looking at it face on. Right? So we have this triangle here, and then we're given this value for h, and that's measured from the tip at the bottom to the level of the water. So this is given to be h. Okay, what else are we given? Well, really, this is the height that we're given. And this up here, this is the base. I claim that the base is equal to h. Why is that true, you might be asking? Well, we need to remember our geometry skills. Whoops, that is not a good triangle. Well, okay, I can't draw triangles apparently. This Notability isn't even recognizing that I'm drawing a triangle. There we go, okay. So I've drawn the base of the apparatus that's holding the water. And then water fills it up to some level here, right? So this is all water. I claim that this blue triangle is similar to the black triangle. And it's basically an exercise to figure out why that's the case. But the logic is that both triangles are isosceles, they share an angle in common, and then we can do some geometry there to figure it out. But we're given that this is h, this is b that we're trying to solve for, and we know that this is 3 and this is 3. Or rather, sorry, that's not 3. We're given that this is 3. So bisimilar triangles, base over height equals 3 over 3. So that means that 3b equals 3h, which tells us that base equals height. That's why I put the h there. So the area of the base is equal to 1/2 times h times h. Cool. So what does that tell us? Now we can compute the volume of the water. So volume of water equals area of base times height. And we computed the area of the base to be 1/2 times h. And the height, well, that's this thing here. And that stays the same the entire time because that's part of the tank that's holding the water. And that's that 12 feet given to us. So we multiply that by 12, and this just simplifies to 6h squared. So that is the volume of the water when the water is at height h. Okay. Now what do we do? Well, now we'll solve for what we want to solve for. We want to solve for dh dt. So let's use implicit differentiation. 6h squared. So we'll take the derivative of both sides with respect to t. And we'll see, actually, I'm going to take out the 6 term before. And we see that this is equal to dv dt. That equals 6 times, I'm going to do a lot of steps quickly here, 2h times dh dt. Very similar thing as always, a mixture of chain rule, power rule, implicit differentiation all in one. I won't explain that one. But yeah, so now we have a function that contains dv dt, h, and dh dt. And we're given h and dv dt. And we want to solve for, well, we want to solve for dh dt. So we can isolate dh dt. dh dt equals dv dt. This is 12h, so we divide both sides by 12h. And now we can finally conclude when h equals 1, dh dt equals dv dt is 2. That comes from up here. And then 1 over 12 times 1, that is 1/6. And then our units are feet per second. And that is our answer. Wow. So what is this saying? Let's put it into context. We have this random tank here, right? We have some dimensions about it. And we know how fast water is entering that tank. And just by that information, we are able to say when the height of the water is 1 foot, when the depth is 1 foot, the height of the water is increasing at 1/6 feet per second. So that's pretty cool. Also, if instead we were given how fast the water height is increasing, we could figure out how fast the water is entering the tank. So lots of really cool stuff we can do here. All right, we have just a couple more problems, and luckily this one's a multiple choice question, so this doesn't look too bad. And this is just a simple implicit differentiation because we see a function in terms of x and y. So let's do it. We have 3xy equals 4x plus y squared. We'll use our handy dandy trick of differentiating on both sides. And now we are differentiating with respect to x. So we've done a lot of stuff with t, but now we go back to x. So we take the derivative of the left, that equals the derivative of the right. I'm just going to distribute the derivative, right? And now things get interesting here. Let's do the right-hand side first. The derivative of 4x is just 4. Derivative of y squared with respect to x is 2y times dy dx. That's power rule, and then you de-stuff the inside. But now we need to figure out what is the derivative of 3xy. Well, that seems like a job for the product rule. So that's what we'll do. The first term, I'll let that be 3x, and the second term can be just y. Or rather, to make it simpler, let's bring the 3 outside, right? I'll just do that here as well. 3 times that. And then let's just compute the derivative of xy, right? And we'll use the product rule. So first times the derivative of the second plus second times the derivative of the first. So d dx of y is simply dy dx. d dx of x is 1, so that's just x times dy dx plus y. So now we substitute and we get 3 times x times dy dx plus y equals 4 plus 2y times dy dx. Let's simplify this a little bit. 3x times dy dx plus 3y equals 4 plus 2y times dy dx. And remember, we're solving for dy dx. So we have to isolate the terms with dy dx onto one side. So I'll keep this first term here, but then I'll take this term and subtract it from both sides. So this is minus this, and that's equal to 4. This term stays, but then this term should go onto the other side, so we subtract 3y. And then from here, we can factor out a dy dx. So that's equal to 3x minus 2y times dy dx. That's equal to 4 minus 3y. And finally, we divide by both sides, on both sides, and we get that as our answer. And if we look at the answer choices, none of them are correct. So what did I do wrong? Nothing. I got the correct answer. And this is where sometimes we have to be careful. We can sort of cross out a couple of answers. Like C just looks wrong. The denominator is a 2. That just doesn't seem right. B looks wrong. That just doesn't feel right either. A, maybe. D, maybe. E, maybe. They all have like the right terms. And it's kind of silly, but you just have to realize that this is negative 1 times 3y minus 4, all of this over negative 1 over 2y minus 3x, and then the negative 1's cancel, and then that's 3y minus 4 over 2y minus 3x, and that's equal to d. I mean, it's just unfortunate that that's how we had to solve it. But it's a good lesson. It's a really good lesson that even if you feel very, very confident about your answer and you don't see your answer on the multiple choices, don't just go back and try to solve it again. Take a moment to see if any of the answer choices are an equivalent form of your answer. Because sometimes people solve it in a different way and then like there's an extra term and a different solution, but it's still an equivalent thing. So don't give up right away if you don't see that your answer matches it. Just take that extra second to make sure that it's the same. All right, and now we move on to the last question of the day, and it is a multiple choice question, but it's a word problem. It's been a long day, so thank you for tuning in. But let's get this last question out of the way, and then next week we'll move on to even more exciting stuff. So the height of a cylinder is 12 centimeters. Radius is 4 centimeters. Circumference of the circle is increasing at a rate of pi over 4 centimeters per minute. The height of the cylinder is increasing 4 times faster than the radius. How fast is the volume of the cylinder changing? So what are we trying to solve for? dv dt. Hopefully that is self-explanatory. We're given the circumference, which I'll just say dc dt, is changing at pi over 4 centimeters per minute. Okay, and then we're given the height and radius of a cylinder. So let's just draw a cylinder, and I'm not very good at drawing, as we've seen. So we'll do one of these, we'll do one of those, and then something like that, okay? It's not the best thing in the world, but it'll do for now. So we're given that's 4 centimeters. We're given this is 12 centimeters. And we also have to take care of this thing that the height of the cylinder is increasing 4 times faster than the radius. So that means dh dt equals 4 times dr dt. Okay. So now we want an equation that takes care of, well, a lot of things. We have volume, circumference, radius, and height. So let's deal with the circumference first, right? So circumference equals 2 pi r. And we have dc dt and dr dt kind of. But let's just see what happens when we differentiate both sides with respect to t. d dt of c equals d dt of 2 pi r. So that tells us dc dt equals 2 pi, which is a constant, times the derivative of r with respect to t. Right? So that's actually pretty nice, because, well, we're given dc dt, right? We're given that that's pi over 4, and that equals 2 pi times dr dt. And that just tells us, solving for dr dt, we get that's equal to 1 over 8. And our units on that should be centimeters per minute. Right? So now we have what dr dt is. And really, now we also have dh dt, because that's equal to 4 times dr dt. So that's equal to 4 times an eighth. So that's 1/2 centimeter per minute. Cool. So now we can consider volume. So we use volume equals pi r squared h. That's the volume of a cylinder. And we'll do our similar technique of differentiating on both sides. And we get pi r squared h, right? So the left-hand side is dv dt. The right-hand side, oh boy, it's pi times the derivative with respect to t of r squared h. This looks like a job for the product rule. So let's do that. H, so your first times the derivative of the second. So I'm going to do it in one step. Derivative of h with respect to t is dh dt, plus second times the derivative of the first, d dt of r squared. Power rule on r, d stuff dr. So let me just simplify this a little bit. R squared times dh dt plus 2rh times dr dt. So that tells us that dv dt equals pi times this huge quantity, r squared times dh dt plus 2rh times dr dt. And everything we have, well, we can substitute into this to solve for dv dt, right? We're trying to solve for dv dt. Well, yeah, that's it. We're given the value of r. We're given dh dt. We're given dr dt. We're given h. So let's solve for it. dv dt equals pi times, the radius is 4 squared, times dh dt, we solve for it, it's a half, plus 2 times, the radius is 4, the height is 12. dr dt, we solve for it, it's an eighth, right? And if we compute that out, we get this is equal to 20 pi, and then the units on that are centimeters cubed per minute. And that is our answer for dv dt. Answer is D. And just like that, just from like some basic data, the size of a container and how the circumference is increasing and how the height and radius are decreasing with respect to each other, we can figure out how fast the volume is changing. I think that's pretty exciting right there. And that's going to be all of the problems that we had for today. So let's just go back to differencing. So yeah, that is our lesson on the intro to derivatives. It was a two-part lesson because this is a very, very important topic. So hopefully you've really started to get the grasp of how to compute derivatives. I know chain rule can be a little bit daunting to do quickly, but just go through the steps that we've been going through. Remember, you have to take the derivative of the outside multiplied by the derivative of the inside. Go back to that formula where we have the derivative of f of g of x is f prime of g of x times g prime of x. If that helps you, do it. Remember, just be very careful with what you're doing so you get the right answer. At the end of the day, it's all about getting the right answer. It doesn't matter which steps you take. If you're very comfortable with taking derivatives, go ahead. I mean, do it. Just be careful. So yeah, that's the end of the intro to derivatives. Hopefully that was helpful. And next week we'll be moving onwards to some more exciting stuff. So I hope you enjoyed. Hope you learned something new. Just as a quick reminder, tomorrow we'll be Physics C. So if you're taking AP Physics C, feel free to tune into that live stream, which is occurring at 9 p.m. Eastern. And yeah, we will be doing this every single week. So thanks for tuning in, and until next time.